After having understood this concept of what happens to a mass at a depth, let's expand it further to understand what is the behavior of gravity with height. So if this is my earth again with the radius r and the object is at a height of h from the surface of earth, I can simply write the force equation as, and always keep taking a very close look at what I am writing here. I am writing the scalar component of vector, which means the force always has a direction. And this you should never forget, because otherwise there will be always a confusion about vector versus scalar. So once this is the case of F bar, I can write it as G m, right, into m upon r plus h whole square. Right? Now I also know mg, which is the force exerted on the surface of earth on the same object, is simply gmm upon r square. So I am going to substitute gm upon r square here as g. So I get, therefore, this implies gm is g into r square. Substituting it here, I get F bar as g upon r plus h square r square. Okay? Now I will take it down to say mg upon 1 plus h by r whole square. This is not of any practical use to me because this equation is very complicated to solve. Right? I will make one more simplification. This is the denominator. Now the Taylor series expansion tells me a very simple thing, that I can resolve it as a polynomial, which means I can simply write it as 1 minus 2h upon r plus nc to all the higher order terms. But we know that for height which is very less than r, because radius of earth is almost 6,400 kilometers, and if we are looking at a maneuvers which are say 1 kilometer, 10 kilometers, your height is very less than r, so h by r is very small. So the binomial expansion of this, I can truncate all of these terms and make it simply as approximately 1 plus minus 2h upon r. Substituting it here, I get mg 1 minus 2h upon r. This is the simplified expression for an object at an height h. So if I try to plot this now, the acceleration g, I can take this out if I am looking at it as an f by m bar, the acceleration. At r, h equal to 0, of course I get g, right? So I will write this as g. Say h is equal to 0.1 of r, I get 0.2, so it is 0.8. So it keeps dropping down. Imagine h tends to r. I cannot plot it here because this assumption falls apart, but hypothetically imagine h becomes r, then this becomes negative. So it has to break down from here. This also tells me that this equation approximation is valid up till h equal to r by 2. Beyond that I anyway cannot use. So this is approximately the plot. These two concepts of at height and at depth brings me to the next third problem of looking at earth as a sphere and having different longitudinal sections where this object is going to be located. So as we discussed, let's now take a look of earth as a component resolved around each of the longitudes and latitudes. So on this earth, there is this object. This is my equator, very standard equator. There is an object at altitude theta. Right? What are the forces that will act? One force that will act is because of the centrifugal motion, the centrifugal force, because earth is a rotating frame of reference. Right? So m omega square upon r. And other which tries to bring it down to the center of earth. Right? So if I am on this frame of reference, it will be this. This is my mass m. So this is the gravitational force, gmm upon this r square. Now this r is not capital R, but this is a small r, which is this, and this angle is theta. So this angle is pi minus theta, because if I look at this angle, it is an obtuse angle compared to it, so pi minus theta will be this angle. Which means I have to get the resultant force, I have to actually add these two vectors using the standard cosine formula, right? So to get the cosine formula, what I do is effective force F bar will be F1 square plus F2 square plus 2 F1 F2 cos theta. The cos theta is delta here, which means you have to have a cos theta angle. So here theta is pi minus theta, right? Which means it is going to be minus cos theta, because cos of 180 minus theta is something like that we have to work it back around. F1 in magnitude is simply mg and F2 is m omega squared r, okay? The radius vector. If these are the cases, I get simply this as the first two expansion terms plus 2g into omega r, because that's the omega square r component, cos of pi minus theta. This expression on further simplification has to come down to a point where I can substitute this back. So I can write this as correct. This expression is simply the product of these two coming down together and giving me the final result as g1 plus omega square r. So it has to be r upon g, right? This is the main governing equation, which means at a latitude or a longitudinal section, when there is a particular plane where there is an object on which the force is acting, the effective acceleration of gravity is a component of these two. Implication. This, so far we saw, does not have any angle of theta, right? This is only valid when theta is equal to 0, because the cos theta component was not there in this. So as a function of cos theta, it will be simply 1 minus 2 upon 2g, right? Because that's what you will get it from here. Now, what we are going to do is basically, we will take this out. At theta is equal to 90 degree, this entire term vanishes, which means if this is my earth, theta equal to 0 is equatorial plane, theta equal to 90 is pole. At pole, g dash is g. There is no way it can change simply because your total theta at cos 90 becomes 0. Equatorial level, you get an additional component of centripetal force or a centrifugal force in the rotating frame, which means because earth is rotating, you will always experience slightly more gravitational acceleration because of this. Question. A question on this can come as an objective question in GATE, where they will ask you what happens if earth stops rotating tomorrow, which simply means omega goes to 0. We now know that at a polar level, there is no component of omega itself, because this rotation of earth is not making any difference altogether. So stopping of earth rotating will have no effect on poles. But at equator, when this goes, gravity will go down. So you will feel less heavy. The weight will actually reduce. And this is a very interesting thing, because this has an implication on inertial frame of reference versus rotating frame of reference, particularly when you are trying to settle an object in an orbit. Because an object in an orbit, say imagine this is earth very small, looking from a distance of very large orbit, wherein you have a spacecraft moving around. This spacecraft on its own also has its own omega dash, because you always have to maintain that spacecraft in that frame of reference by having a right rotation. And now you brought one more satellite which wants to dock, which is called a docking, right? Which wants to dock with this. In the frame of reference of Earth, it is extremely complicated to solve these equations, purely because this g dash effectively fed by this mass is extremely complicated. If I set on this frame of reference, for me, I just have to match the relative motion between the space station and the mass that is going to get docked. This is what is either that you must have seen in Spacestellar or Gravity movies. The Interstellar movie also has this, right? Where you want to dock your small spacecraft with the big space station. The relative omega has to get adjusted so that in that frame of reference, the gravity becomes this g equal to g dash. and then the docking can be perfectly done by even backward thrusting. So this is the beauty of even simplistic equations like this and the applications what they do. Let's take a very simple, very fundamental question which was asked in one of the GATE exams. It was asked that there are two planets, planet 1 and planet 2, which have acceleration g1 and g2. Okay, the constants g1 and g2. In both cases, one person who was crazy enough actually went on the surface of it and threw a stone upward with initial velocity u. In both cases. First one, and he measured a clock on a clock. You don't have to go into Einstein's relativity equations on whether this T1 and T2 were relative absolute. Simply, in a Newtonian frame of reference, he measured that it took T1 seconds for it to go up. Here, it took T2 seconds. What is the relation between G1, G2, T1, T2? And options given were something like this. One option was G1 equal to G2, T1, T2 square. Another option was G1 equal to G2, T2 by T1. Another option was G1, T2 equal to G2, T1. And last option was G1 equal to G2. That is independent of time. To solve this question very simply, we have to very easily understand this. This object started its motion at initial velocity u. Now the equation of velocity change, that is v equal to u plus at, is coordinate frame invariant, which means nothing to do with which planet you set out, right? That's the simple equation of arithmetics. In this case, on planet 1, it must have reached certain height h before it lost its entire velocity because of acceleration pull. So at this height, some h dash, its velocity becomes 0. This velocity must have become 0 in T1, which means 0 equal to u plus g1 T1. And this plus sign will become negative because this is a gravitational pull, which means g1 T1 is equal to u is equation that holds true on this planet. On this another crazy planet, whatever must have happened between the motions, still the velocity equal to 0 must have held true in time t2. So v equal to 0 equal to u minus g2 t2. This means g2 t2 is also equal to u. If you look at these two equations, you will simply come to know that this option is gone because it has to be linearly proportionate. This is gone because it's definitely function of time. Square component of no value. This is the correct answer. G1 T1 equal to G2 T2, which tells me that it is dependent on both the parameters. And that's how you have solved one GATE question. Let's look at one more GATE question as a practice so that all the three concepts we learned are dusted finally completely. In this question, what was asked is you have this big planet, right? Some alien who was crazy enough and had no work to do thought of creating a dig of depth d and transfer that entire mass here to form lump h. Somehow intuitively that alien knew that probably this mass that he will dig out will not be enough to create h of same magnitude. His objective was when his spacecraft lands here, he should have a gravitational force F, the pull, same as when it lands here on the lump. God knows why, but he wanted this. What is the relation between d and h for the same force? Whatever crazy this question may sound, fundamentally we have to understand that in all of these questions, the main agenda to understand is about how do you solve gravitational equations. And we now are master after looking at this of depth and height equations, right? In this case, what will happen is the force F bar that in the dig we will look at is simply 1 minus d by r. We know that, right? Because when d equal to r, everything has to 0. We have already looked at this relation. F dash here was approximately 1 minus 2h upon r. These both have to match, which means 1 minus d by r equal to 1 minus 2h upon r. Both go. You simply get d equal to 2h. So the lump or the hump he has to create on top just to match this crazily is double the size of the depth he will create. Simply because gravity scales down linearly but scales up with the constant of 2 as you increase the height. That's the concept that we have looked at. So to summarize, we have understood how the gravitational pull is between the two objects. How does it behave linearly with respect to height and depth? How does it vary with respect to the angles or the azimuths in terms of equatorial planes? And therefore what happens if the rotation stops? This is the foundation of our spaceflight mechanics, and using this foundation we will now go into understanding more of gravitational potentials and velocities. Now, having looked at how the gravitational acceleration behaves, we have to understand two simple concepts of gravitational potential and gravitational intensity or gravitational field intensity. We have seen that this gravitational field is a vector field of mass of capital M centered around having another small mass m has an attractive force, and this is a field, which means as it keeps coming closer the force of attraction goes up, right? You must have seen, because if you are very close to the earth and you keep coming close, it tries to come down. That's why the stone which you have thrown up comes down on the surface again. Now, this field on its own is very difficult to express, because first of all, it is vector, so you have to take always the module with the theta and the cos direction component of it, if you really want to ensure that you are actually calculating the magnitude. Second, because of the field being a vector property, it is very difficult to perform integrals or differentials, because direction always causes a problem. So two concepts which help us analyze qualitatively the same behavioral motion of any object without going into vectors is what intensity and potential are about. Now, what is gravitational field intensity? Gravitational field intensity is basically an object which is at infinity in the universe brought to a certain distance r and the work that it performs. So if this is my mass m and another mass is lying at infinity ideally the acceleration or the velocity or anything is zero, right? And so does force, because it is inversely proportional to r square. So at r tending to very high values, this is almost negligible. Intergalactical interaction is almost zero. So once this is there, it slowly starts coming together. So it starts reducing the distance, the force goes up, goes up, goes up and becomes more. I want to integrate this property. So Gm upon r square, that's the magnitude, into dr, right? This integral is something called as E. The integral of force field from infinity till a particular distance of r. Right? This is from infinity to r. Now this integral is very simple. It is minus 1 upon r. So the limits are infinity to r. So this at infinity becomes 0. Right? So this simply becomes minus Gm upon r. This quantity is nothing but the field intensity of gravity. This, if you want to correlate, you have to look at something called as electrodynamic potential or electrostatic potential. When there is a charge, another charge which comes from infinity to this point also experiences something called very similar function. The intensity therefore is the embedded energy of the field that attracts and brings that other object into this vicinity. That is the fundamental implication of gravitational intensity. Let us now look at what is gravitational potential. Okay? Gravitational potential is also nothing but energy stored in the field. I have written same formula. Why? Because intensity by its definition is the embedded energy to do this object's maneuver from infinity to r radius. Potential is nothing but same. It is a scalar quantity which brings that particular object to a particular radius r from infinity and stores this much energy into an object. In simple terms, let's look at Earth and a body which is at a surface of r. This body is in equilibrium because the surface provides equal reaction and to its force mg. Right? It is in equilibrium. But since it is residing at distance r in the field of Earth's gravitation, it has embedded energy which is potential. This is minus Gm upon r. That's the significance. Now, if this object from R moves up to height h, right? V1 at rest was minus Gm upon R. V2, when it moved to h, is simply minus Gm upon R plus h, which means delta V, the difference between the two magnitudes, is Gm upon right? Because this is V2 minus V1. What has changed? So it is simply R minus H on R plus H. So delta V is R plus H into Gm. I can substitute Gm from mg equation, right? The force F equal to Gm upon R square, which is mg. So I can take this out and say Gm upon R square is g. So I substitute Gm, the constant normalized, by gr square. So I get delta V as g R square h upon R plus h. Look at slightly how the complicated behavior of potential has become with respect to height. If I bring this h in the denominator, I get delta V as g R square upon h goes down here. So R by h plus 1. Which means as height keeps increasing, denominator starts to dominate because h becomes 2r, this becomes slightly smaller. H equal to r, this is maximum, right? So if I want to plot, when h is equal to r, that is, it is not lifted up, this becomes 2. So delta V is still there, right? And as it keeps increasing towards infinity, delta V goes to 0. Which means the embedded energy, the entire embedded energy gets released when it goes out extremely far field from the gravitation of the object. This is of important significance because when you look at something called escape velocity, you are actually going to escape the gravitational field of Earth or a star or any other object. To do this maneuver, the energy that has to be overcome is computed from here. And that's the significance of this concept. Having now understood all of these concepts of gravitational acceleration, its behavior, the intensity and potential, we will take a small tutorial where 3 questions will be solved, and those questions of gate equivalence will help us test this concept in a concept.